Okay, should be recording. Let me hand it over to Group 9 and let them give us their presentation.
All right, thank you. Hello, we are HelioSmart, and today we'll be presenting our design for a small-scale heliostat. The members of our team are Adrian Arias, Jared Cox, Olivia Dodge, Zariq George, Christian Hooker, Abraham Sheikh, and Noel Turner. The drive behind our design when engineering this product was reducing the number of motors used to create a practical, simple design with novel materials that eliminates unnecessary waste and maximizes profit while reducing cost. We meet these priorities while assuring the customer a 20-year product lifetime in desert conditions in Las Vegas. The design that we created is measured and meant to be a part of a solar plant in Nevada, as requested by the customer, and is engineered to overcome current obstacles with small-scale heliostat implementation, with the overall goal of making heliostats commercially available.
Our module design consists of 2 sets of double mirror heliostats for a total of 4 reflective surfaces actuated by 3 mirrors per module. The footprint of our design is 1.2 meters by 1.6 meters, and the reflective surface are silverback glass mirrors, which allows for the field to generate 1 megawatt of power. PVC has been implemented throughout the base, controller box, and poles to cut down on total cost. Next. The actuation system consists of 2 servo motors to provide mobility in the tilt axes and a stepper motor belt system that drives both of the vertical poles in the azimuthal direction. The controller feedback subsystem is comprised of a Arduino Uno with Wi-Fi capabilities and a motor driver for our 3 motors. As far as the structure subsystem, this includes the base with flanges and rotating poles, and they are both made of injection molded PVC. Next. So one of our unique design characteristics is the use of a lazy Susan bearing. And this is a special type of ball bearing where 2 surfaces are allowed to rotate relative to one another. So the bottom surface is attached to the base and is fixed, while the top surface is attached to the vertical pole and rotates. This bearing provides freedom to rotate while keeping our costs relatively low for the actuation system. An additional unique design characteristic is the gear to pole connection. And this is a gear on gear connection between a spur gear that is actuated by the servo motor and the embedded grooves on the reflective surface shaft. This shaft is supported by 2 ball bearings that are that allow the shaft to rotate. Next. Our ground structure is another unique design feature, and this consists of an injection molded PVC base with flanges. And these flanges prevent the structure from rotating in the soil, while the flat base counteracts uplift forces that may be present due to wind. And I'll pass it over to Jarrett now to talk about the reflective surface subsystem.
The reflective surface subsystem meets the customer needs through the use of 4 square mirrors, and each heliostat has an area of 1/4 of a square meter. The plane mirrors are silver-backed glass with an ABS support and a reflectivity value of 95%. The power needs are met through the use of at least 1,627 modules throughout the whole field. Our reflective surface design shows the silver-backed glass with the 95% reflectivity. There's an ABS backing to provide support for the mirrors, and a C-clamp connects the PVC support rod to the reflective surface and the actuation system. The reflective surface has an optical efficiency of 71%, considering the reflectivity and the cosine losses. The solar radiation flux of 866 watts per square meter was calculated for the winter solstice, which is when the lowest maximum elevation of the sun in the sky. The needed useful input power is at least 1 megawatts per the customer needs. In order to achieve this, even on the worst day, the field needs at least 1,627 modules. With this, the total solar power before losses is 1.41 megawatts. With the use of 1,627 modules, the geometric concentration ratio is equal to 1,627 suns, as each module has a reflective area of 1 square meter and the receiver has an area of 1 square meter. The lift force on the reflective surface was used to determine the safety mode for the module. This was calculated assuming the maximum recorded wind speed in Las Vegas of 90 miles per hour. And the safety mode will have an angle of attack of 0 degrees or parallel to the ground. But we have at least 2 degrees worth of leeway for accuracy of the safety position, which accounts for the ground not being completely flat.
For the actuation subsystem of our design, we put considerable effort into meeting the customer criteria. The tracking error was reduced through the use of high precision motors, and the cost was brought down specifically by using less expensive motors where less torque was required for actuation. All parts used to actuate the model are also very durable to ensure that they will stand the test of time. Now moving on to the actual mechanism for the actuation. The rotation in the azimuthal plane utilizes a NEMA 34 stepper motor that can supply a 4.8 Newton meter torque to the system. This is accomplished through gear-on-gear contact. A gear is attached to the stepper motor, which in turn meshes with grooves on the vertical poles. And once again, the vertical poles are allowed to rotate through the use of the lazy Susan bearing that is attached to their base. Both poles are actuated by the same motor using a belt system. A polyurethane drive belt is used to link their axes of rotation in order to, again, cut down on the motor costs. In the tilt axes, 2 servo motors are each used to control 1 pair of heliostats. The servo motors, again, make use of gear-to-gear contact between a spur gear attached directly to the motor and the grooves that are manufactured into the reflective surface supports. The reflective surface support is allowed to rotate through the use of the ball bearing, as previously mentioned. Moving on to the actuation subsystem design analyses. We calculated the required torque for all motors to withstand any forces that they might be subjected to, particularly the wind force that is generated on the heliostat mirrors. Assuming that the heliostat mirrors are positioned vertically and that the wind force only acts on 1 mirror on each side to consider higher torque, a worst case scenario, in other words, when there is no counterbalancing. The wind force calculated using these assumptions is about 3 newtons, and the torque that acts on 1/2 of the mirrors using this average wind speed is about 2.125 Newton meters. For the motor torque that the stepper motor can generate, again, it's 4.8 Newton meters, and using a gear ratio of 1.14 that was used in the design, the motor is able to generate an effective torque of 5.486 Newton meters to rotate the entire belt and pole mechanism, which is more than sufficient to counteract the wind under average wind conditions. At greater wind speeds, as previously mentioned, the mirror is made to assume a safety position where it moves perpendicular to the ground to negate most directional wind forces. Now, moving on to the second axis of rotation that our system is capable of, we calculated the required torque for the tilt axis to have to protect against wind. Once again, using the average wind speed of about 3 newtons, we calculated the torque. Considering that the wind only acts on the upper half of the mirrors, once again, to consider a worst case scenario in the case of no counterbalancing to the system. And the torque produced by the drive gears in this case, which is again 3.14 Newton meters, is sufficient to counteract the wind force for this axis as well. We included one more calculation in the actuation subsystem design, which was ensuring that the motors could provide sufficient torque to negate the effects of gravity on the mirrors. The weight of 2 mirrors is about 7 kilograms when they are attached to the pole, and considering the position where they are held vertically with respect to the ground. This creates a gravitational force of 68.18 newtons, and the torque that the motor would have to exert on the system in order to counteract this would be 1.73 Newton meters. Once again, using the gear reduction for the top gears of 1.6, we were able to supply a torque of 3.1 Newton meters, which is once again more than sufficient to support the load produced by gravity on the mirrors. And now I'll hand it off to Abraham to describe the structure.
All right, thank you, Adrian. So for the structure subsystem, we have several needs and metrics following them. So to deal with the 4 to 16 heliostat metric need, we chose to do 4 reflective surfaces as stated before. However, one difference is that we wanted to make sure that the nose shading from other heliostats condition was met, and the minimum spacing condition for that was 1 meter or 1.07 meters to be exact. Cost is another important need that needs to be met. In order to do that, we implemented the use of PVC material structure, and the total area ratio is proportional to the structure as well. The factor of safety, that is a need condition. A factor of safety of 2 has been met and has been found through a set of standard analyses that we completed. And the overall operational lifetime of 20 years, that is achieved essentially through the proper material selection. So in this case, PVC, and we believe that PVC will hold up under thermal and environmental conditions and should last over about 20 years with proper maintenance as well. Moving forward, we have the structure design. So essentially, this is to give you a better idea of how the entire system works up until everything we talked about. So if we go from the bottom up, we see that that's the bottom structure, and the arrow shows what is underground and what is above ground. So what is underground is that bottom structure. That is going to be buried underground to hold the heliostat in place and to stop it from moving. Once we go up, we notice that there is a motor mount and motor mount enclosure. The motor is not fully enclosed. It's just to allow it to fasten properly. And the gear on top is also shielded away from any dust or any sand. To separate the rotations between, I guess, the structure and the top pole of the heliostat, we implemented, as stated before, the lazy Susan bearing. That is essentially where it goes. That allows the bottom structure that's underground to be fixed and the top part to rotate and allow for full control and full rotation. And then we noticed that there's a machine notches in the top pole that the drive belt is connected to. And then going up, we noticed that, so we have 2 heliostats essentially, and they are both staggered in height. The tallest one is about 44.55 centimeters tall, and the other one is about 33 centimeters tall as well. Then once we're going up, we notice that the ball bearing, that's where the reflective surface essentially sits, and it's covered. The shielding to protect the gearing from any sun or any dust as well. So moving forward with the calculations, if you could please go to the next slide. Cool, thank you. So in this, so 2 assumptions were made. We use the typical wind speed, or the average wind speed found in Las Vegas, to be about 10 miles per hour. Another assumption was that we use the height of the tallest pole in these calculations as well. So typical wind force on each mirror was found to be 3 newtons. The bending moment per pole was about 2.67 Newton meters. And if you go next slide. Alrighty, so Over here, we find that the cross-section of the pole at the second moment of area was found. From there, we calculate the bending stress of 37.8 kilopascals. And then moving forward, we found the maximum bending stress at 90 miles per hour, 3.07 megapascals. However, I would definitely like to mention that the maximum miles per hour that was found, that was the maximum recorded in Las Vegas, and we are using that assumption within this calculation. Moving forward. From there, we calculate the torsional shear stress due to wind and found that to be 30.35 kilopascals. The shear strength of PVC is about 5 megapascals. And from there, we calculate the maximum deflection at wind speed of 90 miles per hour. Once again, we're using that max 90 mile per hour wind speed that's been recorded in Las Vegas. And the deflection has been found to be 1.403 millimeters already. And so now I'll pass you off to Zariq to talk more about the controller subsystem.
Thank you, Abraham. So in order to satisfy our customer needs, we chose a comparable Arduino Uno clone with Wi-Fi capabilities and a high enough refresh rate to provide accurate and precise tracking of the sun as it moves throughout the day. Our Arduino clone is well within budget, is Wi-Fi capable, and that is what we have chosen. And to move on to our enclosure design, we chose a hollow PVC box which houses our driver and controller. It is partially buried in the ground with hollow wire tubes on both sides to connect to the motors, both the steppers and the servo motors as well. The lid of the enclosure also is designed to be press fit with the case to provide ease of access and also ensure it is protected against the environment, such as no dust and rain. In order to calculate the heat load for our enclosure, we assume the maximum efficiency of 90% for our electronics, so 10% of their rated power is being wasted as heat. And for our worst case scenario, we assume like the maximum historical temperature of about 46 degrees Celsius that was recorded in Las Vegas, Nevada. So in order to model our system, we modeled it as a network of thermal resistors with our, main sources of heat flux being the heat provided by the controller, which is 19.4 watts, as I mentioned earlier, and also insulation provided by the sun of about 32.45 watts. Our main sources of cooling that we're relying on is the convective cooling provided by the wind, as well as radiative cooling provided by the sky, essentially. And using the equation to see below the figure, we're able to calculate an inside temperature of about 118 degrees Celsius. It should be noted that the assumptions we made for this, model was that the system was operating under its worst case scenario. So we're talking about maximum insulation. We assume the cover would be gray, diffuse, opaque, and absorb all the solar radiation, when in reality, some of that radiation would be reflected away. And also we're assuming that the enclosure is in maximum sunlight, even though in most cases it would be covered by the surrounding heliostats. So moving on to our costs, I'll pass it off to Olivia.
Hello. So the total cost to produce a prototype of this design is expected to be about $216.20. Most of this cost comes from the cost of purchasing finished parts, such as the motors and the driver and the Arduino clone. It's also noted that the manufacturing is primarily expected to be injection molding, which is economical on a large scale. And the cost reflected here is an estimated cost per module without the cost of raw materials. The only available quotes we could get included the cost of materials, so we've kind of separated that. And the difference also includes having a smaller quantity size. So there's expected to be approximately 30% in savings for bulk purchases of both the OTS parts and raw materials, which is mostly PVC, bringing the full scale cost to $155.48 per module. Also notable is this comes to a cost of $81.02 per meter squared of module footprint. So that cost can be used to compare it to other energy production methods per square meter of the field. So yeah, I guess in summary, we are presenting the HelioSmart module. What we hope is a sleek and optimized small heliostat module, valuing minimalism and simplicity. So yeah, so thank you for coming. Thank you for your interest in HelioSmart. And we'd also like to thank our teaching team, our professors, and our industry sponsors. If you do have any questions, feel free to start asking.
This is Rick Miles from Northrop Grumman. Just based on what, so you were talking about using Wi-Fi. I mean, Wi-Fi at my house goes out all the time. So could you speak a little bit to the reliability of going with that choice?
So for our, per our customer needs statement, our module is required to be capable of receiving Wi-Fi signals up to 100 meters away. And the controller module that we're using, which is an Arduino Uno clone, as a cheaper version of basically the same Arduino Uno module, comes with a built-in Arduino Wi-Fi shield, which is capable of receiving Wi-Fi signals from those distances. So we expect that the central computing system should be able to provide us just with a steady Wi-Fi signal that our module can receive and then distribute the signals to the motors.
Okay. And then on your mass production costs, so you still came in 155, shooting for 100, right? So
Correct,
could
yeah.
you speak to a little bit to that? If there's any places you see where you could possibly trim some more?
Yes. So our main costs are still going to be purchased costs, purchase parts like our motors. But so we did fall short of the $100 per module. It per square meter of field, it is $81, which is comparable and competitive with current sources. But I think ideally we hope that the added efficiency and effectiveness of our design will make up for that in a sense, to the fact that the more power can be produced over commercially used heliostats now.
Okay,
We are still looking for we're still considering alternative motors and things that can still meet those minimum requirements while also cutting on costs.
And when doing the mass production cost, you talked about it's expected to result in about 30%. Get that, but so what are the assumptions there? So what do you assume a mass production type production is?
So for many of our parts, it's 2 per module. So we're assuming production for the field based on our calculations of having approximately 1,600 modules. We're expecting to make probably around 3,500. So in terms of mass production for the other things, just bulk savings. So that's where we're expecting to find those cost savings. It's mostly working with providers and of retail, I suppose.
Okay, thank you.
On the hey guys, this is Tom Singer. On the belt drive thing, which I really like the concept of moving multiple mirrors with a single motor. I think that's the first design that kind of eliminated the that redundancy. But I'm looking at what appears to be like belt drive teeth or whatever we would call these, machined into a PVC pipe. Where'd you guys come up with that?
So essentially, we didn't want them machined into it. It's injection molded into the pipe itself or the PVC structure itself.
Is this something that's commercially available?
We would have to essentially create that in our injection molding process.
Oh man,
Right.
Why not just like slip a gear over there to interface with the belt and interface with your servo motor?
We consider that. we just thought if less components, less ability to cause any failure or any issues, if we were able to injection mold the whole thing together and put it in these parts, less parts, simpler design. That was essentially the idea of that.
I think you'll find that it's not so simple to injection mold gear teeth in a PVC pipe.
Understandable.
Like I'm not even sure how you would get that out of an injection mold.
Okay. Thank you.
Yeah, I'd definitely think about something slipped on externally.
Absolutely.
Yeah, that causes problems. Your sort of lazy Susan bearing, that's going to be carrying moment from as wind's blowing on your structure. That moment's going to be reactive to lazy Susan bearing. What is that capable of there?
That bearing in particular is capable. It's a very sturdy bearing. So we looked into it. It's capable of supporting axial loads up to about 400 pounds, I believe, and also transverse loads as well.
Okay, yeah, transverse I'm not as concerned with, but when you've got something up on top of a pole, right, you've got a big moment arm for that lateral load to turn into a force couple down at your bearing. I wonder if it would be feasible to move that farther up the post so that you shorten your moment arm.
Yeah, that's another possibility. We would also
wonder what the belt drive kind of interferes with that, but
right, we would probably have to look into moving the motor system upwards as well. But yeah, that is something we could look into.
Okay, and then just to kind of poke at costs a little bit, your manufacturing cost, I think, was I mean, maybe if you were considering injection molding those gears, but I don't think that that's going to be a feasible manufacturing technique. Machining those gears in would cost significantly more manufacturing, and your assembly labor seems pretty low. I mean, you've got to, I guess, glue up pieces of PVC, which is, I mean, it's not super labor intensive, but it's also not something I wouldn't expect somebody to be able to glue this all up. The two posts to glue up the gussets and the base plates, and then fasten these guys to the lazy Susans. I would expect the assembly to take more than if you're paying minimum wage. This is about half an hour's worth of work. I would expect it to be more than that. Maybe you're paying undergrad labor rates.
Hi, yes. So with the assembly labor, we did a calculation for assembly times and fastener times, and it was expected to take about 25 minutes to assemble. Other than attaching the reflective surface to the ABC polycarbonate backing, there wasn't really there is no other adhesive or glue. As much as possible, the parts were expected or hoping to be injection molded together. So like the flanges and the base plate was meant to be one piece, made as one piece. So there's no assembly there. It was mostly motor fastenings, attaching the glass, and then attaching the lazy Susan bearing.
All right, that's maybe a little more reasonable than I was anticipating.
Yeah, thank you though.
What sort of tolerance do you have on positioning and aiming, right? You've got these heliostats arranged in an array around a collector at significant different distance, right? Like what's the max distance that one of these would be away from your collector?
100 meters.
On the ground?
Yeah, so a horizontal distance of about 100 meters from the reflective surface, from the receiver.
Okay, and it's going to be at some elevation, but at least 100 meters away, right? So, with your belt drive system, to and the overall compliance of your structure in in wind loading and whatnot, what is the like positioning tolerance? Like what angle can you maintain, and is that sufficient to point your mirrors at the collector?
So before we came to this current iteration of the design, we looked into positioning like multiple heliostat modules behind each other, sort of in a straight line. And we found that at about 100 meters away, anything over about 2 meters long or so produces enough, I guess, kind of, there's enough of an error margin there that one of the heliostats will miss their target. But with the spacing that we have for the heliostat module as it stands, we don't expect to miss the 1 meter wide receiver target. So we don't have a tolerance per se, but we did look into sort of the minimum spacing that we would have to maintain those modules at in order to ensure that they would both hit the receiver target.
Yeah, I'd wonder, just, as the wind's blowing and it's deflecting things, right? They're going to point away from where you intend to aim them, and I wonder how far away they might be pointing. Whether that's tolerance in the like actual aiming system, whether that is slopped in the aiming system, whether that's compliance of the belt, whether that's compliance of the mirror, compliance of the overall structure. The ability to point at a target 100 meters away, I don't have a good feel for like what a deflection criteria would be for that.
Right. So I believe that we more or less just calculated the total integrated scatter that like one surface would produce. And we, again, like with the minimum spacing, we found that it wasn't significant enough to merit concern about possibly missing the target. But I do understand what you're saying about deflection, like slight deflections and positional accuracy concerning that. So I believe that we would have, we chose our bottom motor specifically so that it had a high enough holding torque to just maintain as much positional accuracy as possible. And then our servo motors obviously have built-in position feedback. So they will be, operating continuously and adjusting to make sure that they're properly hitting the target. So yeah, it would be probably up to further testing and study to kind of address those concerns entirely. But we do believe that with the spacing and the motors that we have, that we should be able to maintain that accuracy.
Brad LaCroix here at Northrop. I had a couple questions about the electronics enclosure. I think the sand itself around the sand or ground itself will actually get quite a bit hotter than the air temperature, so that might be something that's not incorporated into the calculation. And then my other comment is, if it's a press fit lid, how do you get access to it if you need to maintenance or replace one of the components?
So I think how we plan to access it will essentially we'd pry the lid open with some sort of, I guess, screwdriver or lever.
Okay, so it's you'd be able to open it.
Yes, it's not a high enough press fit where.
Okay.
Yeah.
Yeah, it's not meant to be a permanent hold. I think there'd probably be like a small notch on the side.
Okay. And then as far as the belt, I'm a little concerned about thermal expansion and being able to hold the tension on it for to be able to rotate both heliostats. Was there any calculations into how much that would expand, or is there a way to control the tension on it?
So the drive belt was meant to be similar to like a drive belt found in like a diesel engine. In terms of thermal expansion, I don't believe we currently have any exact numbers on that, but I believe polyurethane. It was expected to be reinforced with like nylon or I think Kevlar inside to kind of maintain the structure and the strength. So
Okay.
yeah. So and in terms of tolerancing, it's not meant to be a it's meant mostly to be like a mechanical fit, not necessarily dependent on friction to kind of govern whether or not it turns. It's meant to be like mechanical interaction as opposed to like a really tight hold that would turn it based on like friction.
Okay. Thank you.
Hey, so Alex here, I'll be one of your TAs next semester in Mech 3 if you take Mech 3 next semester. I was wondering about your gear, if you did any calculations about how many cycles that's expected to run in its 20-year lifetime. And also, if this is in a desert, did you take into account sand and like other abrasive material getting in between the teeth of the gear and the belt itself and just wearing away at the belt and the gear?
Yeah, so the gears themselves, we did look into this. At first, we had the idea of 3D printing the gears to possibly, reduce costs and materials and such. And we found that gears manufactured using that process are typically not as hardy as gears made through other processes. So once again, we decided to go through with injection molding and using ABS polycarbonate. So the material is very thermally resistant, and we don't expect it to, degrade in the heat or anything like that. As far as concerns with sand in the environment and things like that, the gears are they do have some protection from the enclosures around them, and they are expected to be maintained regularly with things like compressed air. Things like that. And we did note that they are moving at slow enough speeds to where fatigue failure would not be too much of an issue. Again, most of the forces on the gear would be produced from wind loads due to the wind blowing on the heliostats, obviously, and then causing fatigue failure that way. But most of them are such that other components would fail well before the gears did. So the gears are expected to last quite a long time with the material that we have, and also with the enclosures that protect them, and also through regular maintenance.
Okay, thank you. And just as another note, 3D printing gears usually isn't a good idea because you can't really get the tolerances to line up with what you want to engage whatever you want.
No, I apologize. I meant to say that the 3D printed gears are typically not as with the materials that we would be required to use that are more readily available than, for example, ABS polycarbonate. They are not as resistant, and like the stresses induced in them just due to the way that they're manufactured are more likely to cause them to fail than through injection molding.
Yeah, I was also saying you'll also get a failure where the teeth just won't engage properly because it's a 3D print where it's not as, you can 3D print saying these, it has to be this wide and this angle, but it's not going to be exactly that every time. So over time, you'll fail to engage.
Right, you're right, that as well.
Okay. Any other questions from our panelists? No. Okay. Well, this is actually a good time to wrap up because we're right at 4:45. This is the first time I've ever finished on time. Wow. I'll manage to talk for a minute and go, oh, there, I just went over. There we go. Okay, back to my old ways. All right, well, let's thank the group for sharing their presentation with us. And oh, the other thing I wanted to mention is if for those of you on the panel, you can hang on to your rubrics if you like. The rubric should be the same throughout the week, but if you want to, get rid of it and send it to me in an email, then start with a fresh rubric tomorrow, Wednesday, Thursday, etc. You can shoot those to me in email, and I will just compile them and like I said in the orientation this morning, kind of figure out everybody's grade based on an average composite of all the scores that I get. But I think that brings us to the end of this session. So thanks guys for your presentation. Very well done. Good job. We look forward to seeing your final design report so that we can move forward to potentially prototyping in 4502.
Thank you very much.
Thank you.
Thank you.
Great.
Thank you.
Thank you.